Yes. So in your last class we introduced carbene intermediate. So we learn about how to generate a carbene, that is initiation of a carbene. Carbenes are generally classified into two types, singlet carbene and one more is triplet carbene. So some selective generations we discussed. Later on we also discussed how to identify a carbene, at the same way how to trap. Okay? At the same way carbenes also get stabilized by inductive effect as well as mesomeric effect. Okay? Then this is your last application regarding carbene, chemical reactions of carbene. Chemical reactions of carbene. So what kind of chemical reactions you will expect for a carbene? Right now we are going to discuss. So carbenes involve in, see, cycloaddition reaction. Carbenes involve in cycloaddition reaction. Especially if I take a olefin, when olefin reacts with a carbene, yet this carbene carry 2 electrons. Now this is undergo cycloaddition between these two. Now these pi electrons will attack here and these non-bonding electrons will combine, and finally there is a formation of a ring formation. So this is a cycloaddition. Especially in this case olefin behaves as a nucleophile and carbene behaves as a electrophile. This point you remember. Okay. So the addition reactions between carbene and olefin leads to form a cyclopropane. In this particular reaction, it is behaves as a nucleophile and carbene behaves as a electrophile. Now generally we know that these carbenes are classified into two types. Okay. So first case, singlet carbene addition. This is singlet carbene addition. So what happens when singlet carbene is added? When singlet carbene is added to olefin, this reaction is always a concentrate. Remember, it is concentrate and stereospecific. This you remember. Singlet carbene addition around olefin is a concentrate and stereospecific. So what is the meaning of concentrate? Single step reaction, there is no intermediate. Stereospecific means whatever olefin stereochemistry is maintained, same stereochemistry is going to lead to form after product. Cis becomes cis, trans become trans here. So this is generally observed like this. So carbon-carbon double bond, CH3 I am writing, and here hydrogen and here hydrogen. So what kind of olefin it is now? Cis olefin. Now I am participating in a singlet carbene. In singlet carbene, what is the orientation of two electrons? Same spin or opposite spin? Opposite spin. So here it is a anti-clockwise and this is clockwise electron. It is a pi bond, anti-clockwise and clockwise. Now what happens, see, this anti-clockwise combined with this clockwise, this anti-clockwise combined with this clockwise, and finally what you will expect? A cyclic transition state. Carbon-carbon, CH3 and this is CH3, and can you write like this? This is CH2. Now how many different electrons are present? Opposite spin electron, anti-clockwise, clockwise. Can I write a delocalized transition state? Yes. There is a cyclic transition state establishes here, and finally you will get only one product. So what is that product? That is cis olefin. Not even 1% of trans olefin is going to expect in this one. So when cis olefin is given, your answer always a trans olefin, cis olefin, when I use a singlet carbene. Singlet carbene addition always leads to form stereospecific only one product. That's why it is called specific reaction. Suppose if I take a trans olefin, what is the answer? See, this is a trans olefin. Next I am combining with a singlet carbene. So when singlet carbene is added, what is the final answer? C. Now you will get only one product here. Cycloaddition of trans with a singlet carbene always leads to form only trans here. In this case we are not going to get any cis isomer. So stereochemistry of olefin is completely retains in cyclopropane formation. That's why it is called stereospecific reaction. Right. cis become cis, trans become trans. So olefin stereochemistry completely retains in product. That's why this reaction is called stereospecific. Stereoselective means whichever is measured, that will be selective. That's why when you get unequal products, whichever is measured, that is selecting. That is called stereoselective. Specific means 100%. When we use cis isomer or cis olefin, you will get always cis cyclopropane. That's why this reaction is stereospecific. What about triplet carbene addition? Now I am using triplet carbene addition. This is second possibility. Every time two types of carbenes are going to be added. First is singlet, next is triplet. Now triplet carbene addition is, see, this is non-concentrated and non-stereospecific. It is non-concentrated and non-stereospecific. What it means? It is a non-concentrated, non-stereospecific means more than one step. It is a single step reaction. This is a transition state. It is not going to be considered as a step. Okay, but in this case, you will expect a multi-step reaction. Definitely one intermediate is going to be formed in this one. Okay. Now, whenever if I take a cis olefin, carbon-carbon double bond, and here hydrogen and here hydrogen. Now I am taking a carbene. So this carbene having two equal spins or parallel spins or not. Triplet carbene having a parallel spin. Two electrons are orienting in one direction, clockwise, clockwise. On this case, what happens, see, here this is a clockwise and this is anti-clockwise. Out of this, whichever spin is opposite to one of the electron, they will combine first. Suppose here it is anti-clockwise, now it is clockwise. This electron combine together like this. So after formation, two electrons going to be left here now. This is CH3 and here hydrogen, and this is connected to which one? Carbon. Now this carbon carry parallel, here also carry parallel. 1,3 biradical with a parallel spin will be the answer. So after getting this, what happens, see, these two electrons want to combine, but they won't combine. Why? Because they are having a parallel spin. Now two possible reactions are expected. So what are the two possible reactions? In first case, when they come close together, they will repel with each other and one of the electron goes to opposite side. This is called electron spin inversion. Okay, so what is this? Electron spin inversion. This electron spin inversion due to collision. So due to collision of these two electrons, one of the electron spin will be inverted. Once a spin is inverted, what do you expect? See, this is CH and here also I am writing CH and this is CH3. And what about this electron spin here? Clockwise. And what about below carbon? This carbon spin is anti-clockwise. Can I write like this? Clockwise and anti-clockwise. Finally, what is the answer? Clockwise, anti-clockwise get combined together and see, you may get a cis olefin or not. Now this is cis olefin. Okay. Now second possibility, what happens, see, this is spin of electron. Now these two electrons are coming close together. You may expect a spin inversion. That is first possibility. Second possibility, what happens, see, there is a CC rotation will takes place. When two electrons are come close together, so then CC rotation takes place, and second possibility, spin inversion takes place. That depends upon the molecule. Suppose if CC rotation takes place here, now see like this, CC rotation takes place. Then what happens, see, can I write these two electrons with a opposite spin or not? Clockwise, anti-clockwise. Now what is the orientation here now? Same side or opposite side? Same side. Now two electrons having a same spin, if they come close together, two possible reactions are expected. First possibility, one of the electron spin will be inverted, then other carbon-carbon rotation will take place here. So when triplet carbene is added, you will get a 1,3 biradical. So when 1,3 biradical, two electron carbons come close together, two possible reactions are expected. First one is spin inversion due to collisions, then second one CC rotation, then finally cis isomer becomes a trans isomer. So finally what is the answer? Final answer is trans. Most of the cases trans is measured as compared to cis. So now which is measured in this one? Trans is measured or not? And what about this one? Cis is minor. So reason is, key reason is stability. Only stability is the reason to expect major population of trans. Okay, remember, when any kind of olefin combining with a triplet carbene, you will get a intermediate now. This is intermediate in this one. It is a step. After getting 1,3 biradical, these two carbons want to combine. During this combination, two possible ways you can predict. First possibility, spin inversion. When two electrons combine together, then one of the electron goes to opposite side, and one more, due to approach of these two electrons, CC bond rotation maybe rotates, and finally you will get this one. And after getting this opposite spin electrons, you may get a combination of these two electrons leads to form trans isomer. Two pathways you need to remember. Now is it a stereo specific? No, it is not a stereo specific. It is a stereo selective. I am saying it is major. So which carbon addition is stereo specific? Singlet carbon addition is stereo specific. Triplet carbon addition is a stereo selective. I am saying major and minor or not. Major means selective. Minor means non-selective. I am selecting or not. Out of two, which you will select? Major. I am selecting this one. So we can say it is non-stereo specific, otherwise stereo selective. This is pathway, first pathway, and this is second pathway. Spin inversion, CC rotation. CC rotation pathway, and this is spin inversion pathway. So sometimes spin inversion pathway may be major, sometimes CC rotation pathway may be major. That depends upon the orientation of cyclopropane formation. So don't think that always CC rotation is major. This is proposed by Skull. Skull introduced this process. So I will explain one more example, just listen. This is a trans olefin or not? Trans olefin. Now what I am combining now? Clockwise, clockwise. Which carbon? Triplet carbon. Now here this is anti-clockwise, it is clockwise. Anti-clockwise, clockwise get combined together and forms one of the isomer. Can I write like this? Clockwise, clockwise. Is these two electrons combined together? No, they won't combine. Why? Because due to parallel spin. So now what happens, see, now two pathways you need to choose. First pathway, what happens, see here, spin repulsion will responsible to give collision, right or not? Now these two electrons come close together, then they will collide with each other, and what happens, spin inversion takes place. So during spin inversion there is no CC rotation. So then what happens, this is clockwise, and what about this one? This becomes anti-clockwise. Now see, clockwise, anti-clockwise, clockwise, clockwise. Now these two get combined together, and what is this? This is the answer. Is it trans or cis? Now trans. Trans is major. In this case, now one more pathway is there. When two electrons are come close together, they want to combine, but due to similar spin, they won't combine. Then what happens? CC rotation takes place. Converting cis to trans is easy, but converting trans to cis is a delay process. It is not a rapid process. CC rotation. Is it CC rotation possible in this one? Not easy. Possible, but not easy. So finally what happens, see, here you may get a clockwise, and what is this? Anti-clockwise. After this, these two combine together and forms cis isomer. Now mixture of two isomers we are getting now, cis as well as trans. Which is major? Now trans is major. Observe clearly, in this case, CC rotation is predominated as a major product. But in this case, spin inversion is predominated as a major product. It is not depends upon the mode of rotation, mode of inversion. It depends upon the product formed. So whichever direction stable product is formed, corresponding interaction is influenced very high in that 1,3 biradical. Is it clear? Okay, that's why these reactions are called stereo selective. Always which is major? Trans is major. Sometimes CC rotation is dominates over spin-spin inversion. Sometimes spin-spin inversion dominates CC rotation. Clear? So that is cycloaddition. Otherwise you can say addition of carbon around olefin leads to form a cycloring. That's why it is called cycloaddition. So it may also known as chelotropic reaction, one kind of chelotropy. Ring formation takes place with an atom which carry at least one lone pair. So that is develops two new sigma bonds around olefin. It will comes one more time in pericyclic reaction. Chelotropy. Next, insertion reaction. Cycloaddition is over. Insertion reaction. So what is insertion reaction? Insertion nothing but we are inserting carbon between carbon and hydrogen bond. That is called insertion. So inserting carbon in between carbon and hydrogen bond is nothing but a insertion reaction. See, if I take a carbon having 2 electrons, now it is going to be inserted between them. See, carbon having how many bonds? See, this is carbon, carry 3. Now, I am introducing this carbon in between this carbon and hydrogen. So, simply break this, insert between these two. So, then what happens? See, this hydrogen is added to CH2. Now, the CH2 added to carbon. So, this is called insertion reaction. Insertion means inserting between carbon and hydrogen. Indirectly, we are breaking this bond. This hydrogen is added on this carbon. Now this carbon forms one more bond. This is called insertion reaction. So this is best example for intermolecular insertion. Between the molecules, it is going to be inserted. So break a bond between carbon hydrogen. Okay, after breaking, add this hydrogen on carbon and this carbon part will be added here. So simply what I am saying is after breaking, what you will expect? You will get like this or not. It is one radical, here one radical. Okay, now middle carbon is going to come. Now this carbon, how many electrons are present? 2 electrons. Now this is going to form a bond between these two. That is the answer. That's why it is called insertion. Insertion nothing but putting completely, we are inserting carbon within the carbon moiety. So this order will be always remember. Now this is preferred for benzyl, then followed by allyl. Then this order is belongs to tertiary, secondary and what is one more? Primary. This is insertion reactions order. So one example I will give. Just listen, this is a carbon. Now I am giving a hydrocarbon part. This is CH2 and this is CH3. So where you will insert this molecule? Where should I introduce this carbon between these two? Now is it a primary? Now what about here? Secondary, and this is primary. What is the order? Tertiary, secondary and primary. When secondary, primary both are present. Now first break carbon hydrogen bond in normal molecule. After breaking, now what happens? One hydrogen we are removing over here. Now this hydrogen is added here. Okay, then this electron and this carbon electron forms a bond. Can I write CH3? Yes, that is the answer. break bond between carbon and hydrogen. Now write down the CH2 exactly middle, hydrogen carbon forms bond. That is the answer. Okay. Now can you give the answer? I am using a carbon. Now this is a carbon which is connected. This is CH3 and here one more CH3. This is CH, CH2 and this is CH3. So where you will insert this CH2? Now this is primary and what is this? Tertiary, tertiary, secondary. Where you will insert this carbon? Which side you will insert? Now tertiary or not, between these two tertiaries are not same. Try to insert that side where you will expect ethyl group. So it is a powerful donor as compared to methyl. So can I insert towards right side? CH3 and this hydrogen is as it is. Now this is CH3. Can I write CH3 one more? CH3, CH2 and here this is CH3. This is insertion reaction. Now can I introduce here or not? Remove carbon hydrogen bond. After removing carbon hydrogen, now this carbon having a radical. Hydrogen also carry radical. Hydrogen is added here and it becomes a CH3. Then CH3 connected to this carbon forms a new CC bond between two carbons. Now in this case also two types of carbons are expected. So what kind of carbon it is? It may be singlet or triplet. Suppose if it is a singlet carbon. If it is singlet carbon, what is the answer? Is it concerted or not? This point is, remember, concerted and stereo specific, always only one product. It is a concerted and stereo specific. Suppose if triplet carbon is introduced, and what do you expect? Can I say non-concerted? It is non-concerted and stereo selective, we can say stereo selective. Otherwise you can say non-concerted, non-stereo specific. You can say stereo selective, otherwise non-stereo specific. You can use any kind of carbon, singlet or triplet. But if I use singlet, reaction is very faster as compared to triplet insertion. Right. Clear? Now, will you give the answer for this? Suppose if I give cyclopropene, cyclobutene, cyclopentene, hexane. Now I given cyclohexene. Now if I want to introduce this carbon, where should I introduce that carbon? I want to make an insertion reaction. Insertion reaction or not? Where should I insert? On double bonded carbon, allylic carbon, homoallyl, etc. How many possibilities are there? Homoallyl, allyl and double bond. Now suppose if I introduced on homoallyl or olefinic carbon, can I write CH3 here? If I break this carbon hydrogen bond, okay, break this, write down this CH3 middle, write down hydrogen and carbon carbon bond, that becomes CH3 or not. Now one more possibility, what should I write? See, carbon carbon double bond. Now can I write CH3 here? Is it possible? Other possibility, this is CH3 I am writing, is it possible? Can I break this carbon hydrogen bond also or not? Yes. Now can I break this one even? If I break this one, what is the answer? Double bond, and can I write CH3 or not? Now out of these three, which is major? Whichever carbon hydrogen bond is very weak, they can involve in reaction actively. So which is very weak here? Allyl. Allyl is major. So allyl is major and remaining are minor. This question asked in exam. Insertion of carbon around double bond will leads to form a insertion reaction. That insertion reaction will give multiple products, which is major among them. This order you need to follow: benzyl, allyl, tertiary, secondary and primary. This is important for exam. Clear? So that is insertion reaction. Next, third one, rearrangement. Rearrangement of carbon. Carbons also involve in rearrangement reactions. So the famous reaction for rearrangement is Wolff rearrangement as well as Arndt-Esther rearrangement. So listen, this is most important, and complete applications I will explain in rearrangement reaction. Right now I am giving only one example. So carboxylic acid on treatment with thionyl chloride, then what happens? There is a formation of a acid chloride and loss of SO2 takes place, right? After getting this, now I am reacting with one molecule. Can you give name of this molecule? Diazomethane. What is that? Diazomethane. When diazomethane attacks on this carbon, now back to back resonance is going to be appeared. Now chlorine is removed in terms of Cl minus. That Cl minus takes one hydrogen from here, and finally that carbon bearing negative charge. During attack, negative charge disappear. So when chlorine is removed, and that will take hydrogen here, and what is removed here? Hydrochloric acid is removed. Then can you write the answer? RC double bond O. Now what will expect? CH, and then nitrogen nitrogen triple bond, and what is this? Minus. Can I write like this? When this minus attacks here, charges disappears. When chlorine is removed in terms of Cl minus ion, that will take one of the proton and forms CH2, becomes CH anion. Now this is called acyl. Is it acyl group or not? So this is called diazomethane. Now it is called diazoketone. Yesterday name I given, diazoketone. So when diazoketone on photochemically, silver monoxide if I use, photochemical or thermal. Now this negative charge migrate here, this R migrates from here to here, N2 is removed. Okay, diazoketone. What is this? This name you remember, diazoketone. Diazoketone undergo intramolecular rearrangement, and that will give R migrates on carbon, and this is C double bond O. What is this? Ketene. This is also given. This is ketene. Now ketene on treatment with water molecule. Now water is selectively attacks on carbon. Now this electron migrates on oxygen, and one more time it will come back, and this electron transfer to this one. So after transferring, what is the answer? CH minus or not? And this carbon carry double bond O, and oxygen carry how many hydrogens? 2 hydrogens. Remove one of the proton, that will be added here, and finally C, you may get this answer. C, can I write C double bond OH or not? And can I write CH2? So what is this? This is called homologation. Homologation means we are inserting one CH2 group between these two. Okay, see, finally you can write like this or not? RC double bond OH, RC double bond OH is converting into, how it is converted? RCH2 C double bond OH. This is called Arndt-Esther rearrangement. simply between this carbon and alkyl, can I introduce CH2 or not? I am introducing CH2 between C double bond OH and R. Now it is a homologous series of carboxylic acid or not? If I repeat one more time, what happens? One more CH2. If I repeat one more time, CH2. So regularly there is a differ only with CH2, that is called untested rearrangement. What is this rearrangement? Untested rearrangement. Now especially diazoketone to ketene, this you remember. Diazoketone to ketene is known as Wolff rearrangement. If you know this concept, two rearrangements will be in your hand. What is first one? Diazoketone to ketene. I will explain one more time in untested rearrangement separately with multiple applications, but right now you remember some selective names. Diazomethane, and what is this? Diazoketone. Ketene. Conversion of diazoketone to ketene under thermal or photochemically is known as Wolff rearrangement. Homologation of carboxylic acid is known as untested rearrangement. Within that homologation only, Wolff rearrangement is a common rearrangement reaction. If they given diazoketone to ketene, that is called Wolff rearrangement. So this migration is also known as retention of migration. So whatever migration takes place here, now this group is migrating from here to here or not? Okay, now this migration is called retention of configuration. This time in GATE this question is given, in GATE examination. So Beckmann rearrangement and this, a competitive question is common. So migration of group will retain their configuration. So now what is our concept actually? Our concept is carbon or not? Where you observe carbon here? Where actually carbon is observed? See, our concept is carbon. We are learning carbon as an intermediate. I am saying that this chemical reaction includes carbon. So where you observe carbon here? Diazoketone. This is the target site for carbon. So listen carefully. Now I am taking a RC double bond, and what is this? CH minus, and what is this? Nitrogen, nitrogen triple bond plus, right? Now what happens, see, this R is migrating on carbon, observe clearly, R is migrating on this carbon, but this carbon carry which charge? Negative. Is it negative accept this nucleophile? No. So it is not a real nucleophile. Now initially what happens, see, this N2 is removed out first, this is your first step, N2 is removed. When N2 is removed, how many bonds are present around carbon? Only two bonds, one with carbon, other with hydrogen. So now this carbon becomes a acyl carbene. What is this? There is a formation of an intermediate acyl carbene. After formation of a acyl carbene, this R is migrates from here to here, and this lone pair will migrate here now. Okay, now acyl carbene undergo rearrangement. Finally, there is a formation of R, and can I write CH? CH. Now here there is a double bond, and this is C double bond. What is this? Ketene. So first there is a loss of N2, then later on rearrangement will take place. Suppose if this intermediate is a real intermediate, if it is a real intermediate, during this reaction if I add water molecule, what happens, see, that water molecule is going to add it on this carbon. So hydrogen above, hydroxy group is above. Right or not? How water is going to be splits? H and OH. H is added on this radical, OH is added on this radical, and finally forms H and OH, and this is CH, right? So when there is a rearrangement is observed in case of diazoketone, definitely there is a formation of an intermediate. What is that intermediate? Acyl carbene. This acyl carbene accepts this nucleophile. Without acyl carbene, this rearrangement is not possible, but this acyl carbene is not trapped. We are not getting this product. We are expecting this one, but we are not getting. We are expecting this product, it is not getting. Key reason is due to its instability. So it will form this intermediate, spontaneously undergo rearrangement, you will get this one. It is a very fast process. There is no time to trap in the form of like this. So that's why this is a real intermediate, but it is not possible to trap. Why? Already carbons are unstable. To that carbene, what is present? Electron withdrawing group. What is the role of acyl here? Electron withdrawing group. Acyl is withdrawing electrons. Then what happens? Stability increases or decreases? Stability decreases. When stability decreases, trapping is not easy. So we want to trap this intermediate by adding a water, but unable to trap. We are expecting this one, but we are not getting. Why? Why it is not possible? Why? Because already carbons are unstable. To that, if any acyl group is present, stability increases or decreases? Further decreases. Due to highly instability, these carbons are not possible to trap. Okay, but what is the real intermediate? Acyl carbons only. Okay, So finally we can say that loss of N2 migration of R takes place simultaneously. It is not a step-by-step process. Suppose if it is a step-by-step process, intermediates get trapped in the form of alpha hydroxyketone. Clear? So that's why you should write like this. See here. Initially in this case, first I removed N2. Next later on I migrated one group from carbon to carbon. Like this we are migrated, right? But in this case what I did? I removed N2 and I migrated simultaneously. Suppose if it is a step-by-step process, now the intermediate carbon is get trapped in the form of alpha hydroxyketone. This question they asked. In Wolff rearrangement, intermediates get trapped in the form of alpha hydroxyketone or not? Is it possible? No. It is impossible to trap in the form of alpha hydroxyketone. Why? Because it is a simultaneous process. Loss of N2, migration of R takes place simultaneously. But who is intermediate in this one? Carbon. Is it carbons are possible to trap? No. Not possible to trap. Why these carbons are not possible to trap? It is highly unstable. They won't give that much time to react water molecule with this carbon. That's why they are simply escaping and converting into carbon. Finally, Wolff is saying that it is not a multi-step reaction, it is a concerted reaction from year to year. It is one famous rearrangement, Wolff rearrangement reaction. Okay, first you take up to here, then you write, first you take this, then I will give. So if you know carbons, three named reactions are very, very important. First one is untested, next Wolff rearrangement, one more is Siemens-Smith. It will come later, but it is also carbon type of intermediate only. So first you complete up to here. After completion, this you enclose in box. Homologation of carboxylic acid. So after that, you write down this reaction. Carboxylic acids reacts with thionyl chloride. SOCl2 is called thionyl chloride. That will give acid chlorides. Acid chlorides reacts with, what is this? Diazomethane. So what happens when diazomethane on photolysis? Diazomethane on photolysis give carbene. It is carbene. But what I am using as a nucleophile. Suppose if this molecule on photolysis, that will give carbene. But right now I am using as a nucleophile. This nucleophile attacks here and HCl is removed. Loss of HCl. Then what is this? Diazoketone. Diazoketone to ketene is known as Wolff rearrangement. Later on, reacting with water will give acid. Reacting with alcohol will give ester. Reacting with amine will give amide. Many possibilities are expected. Right now you remember, we are converting diazoketone to ketene, later on converting into acid. This is overall reaction, total, untested and Wolf, and this is definition for untested, and this is for Wolf rearrangement. So first you complete, then I will give definition. So some names you need to remember. Why? Because after completion of intermediates, reactive intermediates, I am planning to start molecular rearrangement. If you see in your syllabus, these rearrangements will be there. Untested rearrangement, Wolf rearrangement, pinocol, pinocolone, okay, Wagner-Mervin rearrangement, so Siemens-Smith reaction, etc. So molecular rearrangements, already some select intermediates we discussed. In that one, these rearrangements are going to be covered. Okay, right. Write down one point. Homologation of carboxylic acids. Homologation of carboxylic acids is known as untested rearrangement. ARNDT EISTERT, untested rearrangement. Homologation of carboxylic acid is known as untested rearrangement. EISTERT, untested rearrangement. Next, this is untested. So you focus on the CH2. Okay, next point. Conversion of diazoketone to ketene. Conversion of diazoketone to ketene under thermal or photochemical conditions. Under thermal or photochemical conditions is known as Wolf rearrangement. It is known as Wolf rearrangement. It is Wolf rearrangement. Next, intermediate in this reaction is intermediate in this reaction is, what is that intermediate? Intermediate in this reaction is acyl carbene. Intermediate in this reaction is acyl carbene, but not possible to isolate or not, but not possible to isolate, otherwise trapping is not possible, I am saying. So therefore it is a concerted reaction. Concerted means loss of N2, migration of R takes place simultaneously. So finally we are saying that it is a concerted reaction. Loss of N2, migration of R takes in a single step. Therefore it is concerted. Which is concerted? Is it untested or Wolf? Wolf rearrangement is a concerted reaction. So here what we observed? Loss of N2 and migration of R. Loss of N2, migration of R takes in single step. This is one of the evidence. So in Wolf rearrangement, loss of N2 and migration of R takes place in a single step. So that's why it is a concerted reaction. So one more you can also write C. This is R, CH. This is carbon. This is one more kind of rearrangement. So you will learn clearly in examples. Right now I am giving one more example. Now 3-membered ring I given and carbon is present on one of the carbon. Now what happens, see here there is a possibility of breaking this bond. Now this bond is going to migrate here and this bond is going to break here. Okay, so on this case what happens, see this CH connected to this carbon. Now this carbon connected to CH, then followed by R. So what is the answer? Alene. If this type of carbons are present on cyclopropane, that is responsible to give alene. It is also one kind of rearrangement. Okay, so this is possible under photochemical or thermal. Thermal or photochemically, carbons present on 3-membered ring leads to form alene formation. If this molecule and thermal photochemical symbol is given, you write down this answer. Carbons undergo rearrangement to give alenes if that carbon present on 3-membered ring especially. Clear? That is rearrangement. Next is Siemens-Smith reaction. So only one example I will give. Applications you will see separately. In olefins it will be zinc OMC, it will be. Siemens-Smith also one of the example where carbon is exist as an intermediate. So can I write like this? See, this is olefin, cyclohexene. When cyclohexene on treatment with a diiodomethane, what is CH2I2? Diiodomethane in presence of zinc copper couple. Zinc copper couple. When diiodomethane reacts with zinc copper couple, then what happens? See, there is a formation of a cyclopropanation. Cyclopropanation of olefin to give a cyclopropane by using diiodomethane is called Siemens-Smith reaction. Suppose if any crowding group is present, see where crowding group is present here now, above the plane or not. Now see, I am using diiodomethane, CH2I2, zinc copper couple. Always remember cyclopropanation takes place from opposite side of crowding group. Now where crowding group is present, above or not? Can I write below? That is the answer. Suppose if any chelating group is present in Siemens-Smith reaction, now this is a chelating group. Now always cyclopropanation takes place from the direction of chelating group. So they also involve in chelation. So what is the answer? Can I write like this? This is orienting above and what is one more? Can I write cyclopropane from above side or not? This is above side. These points remember. When competition comes between chelating group and crowding group, always consider chelating group only. Always cyclopropanation directs from the direction of chelating group. So when molecules having more than one double bond, okay, and if the double bonds are unequally substituted, if the double bonds are unequally substituted, see here I am using 2 double bonds here now, right? Out of these 2 double bond, which double bond is more electron rich? Out of these 2, which is more electron rich? Right side. Now what I am doing is I am using diiodomethane in presence of zinc copper couple. Which double bond is get cyclopropanated? Now electron rich double bond is cyclopropanated. Suppose if it is takes place from below, now what is the orientation of methyls? Methyls are orienting from above direction. You should write thick line. Suppose if competition comes for chelating group and crowding group, this is crowding group and this is chelating group. Now one point already just now explained. If any chelating group is there, we are directing from chelation side. If any crowding group is there, we are directing from opposite to crowding. Now here crowding group is above, can I attack from below? So no. But why? Because now it is reaction controlled by chelating group. Chelating group is nothing but which forms a ring with reagent. Okay, so what is the reagent now? Diiodomethane in presence of zinc copper couple. Then what is the answer? So can I make cyclopropanation from above the plane or below the plane? Above the plane. So can I create a cyclopropane or not? This is the answer. When competition comes, not only this one, if any reagent have a tendency to form a ring, always chelating group is a director. Suppose if this chelating group is not present, now this will make cyclopropionation from below side. Okay. Now very important thing is the intermediate in this reaction is, so what is the intermediate involved in this one? See, diiodomethane is combining with copper activated zinc. That is the meaning of zinc copper couple. Copper activating zinc or copper activated zinc. Now in this case, iodine is inserted between zinc and carbon. So this is called iodomethyl zinc iodide. What is this? Iodomethyl zinc iodide. This is also called carbenoid. This you remember. It is a OMC. So what is the real intermediate involved in Siemens-Smith reaction? That is carbonide. Now this mixture responsible to give this intermediate is called carbonide. Now this is responsible to give cyclopropane around olefin. Suppose see this is olefin. Now this mixture is giving this one. So when they give this, you can write like this. This is iodine and what next? This is ZnI2. Okay. Now this is combining with this one. So when they combine, you will get this kind of intermediate. Now see this. This is CH2. Now what is this? This is iodine and what is one more? This is CHI. Okay. And finally this iodine is taken by this one. These electrons are completely transferred to this carbon. So this is intermediate. Now after getting this, what is the answer? You may expect a cyclopropane and what is removed? ZnI2 is a byproduct in this one. Okay, like this a transition state is established here. So I can write a thick line so that you can clearly, it is visible for you. So this is a thick line of carbon. Which one? This CH2. Right? Now here there is a weak bonding between hydrogen and there is a weak bonding between ZnI. Why? Because when this carbon attacking on double bond, these bonds are getting weak. And finally there is attraction between ZnI. And finally this CH2 will be inserted over here in the form of cyclopropane. And what about byproduct? Byproduct is ZnI2. That is the answer. This is mechanism. One more time. It will come in Siemens-Smith applications. There I will give intense applications. Even I will explain asymmetric synthesis for that one. Okay, right now remember, conversion of olefin to cyclopropane by using diiodomethane in zinc copper couple is called Siemens-Smith. When crowding group is there, attack from opposite side. When chelating group is there, attack from the direction of chelating group. If both are present, consider chelating group. If multiple double bonds are present, whichever is more electron rich, only that double bond undergo cyclopropanation. Okay, what is intermediate in Siemens-Smith? Intermediate in Siemens-Smith is carbenoid, also called iodomethyl zinc iodide. Remember this name, iodomethyl zinc iodide, carbon bearing negative charge, zinc bearing positive charge. So this is the mechanism. Take directly. What is Siemens-Smith reaction? conversion of olefin to cyclopropane in presence of diiodomethane in zinc copper couple. You can also say like this: copper activated zinc. Who is activating? Copper is activating zinc to participate, not zinc is activating copper. Who is participating now? Zinc is participating. It is a zinc OMC reaction. It is a zinc OMC reaction. Copper is activating zinc, and zinc is actually inserted between carbon and iodine, and that is giving a carbonide. Iodomethyl zinc iodide is called carbonide. Now the CS2 unit is introduced between these two carbons and forms a cyclopropane. Clear? So this is your last application for carbene, that is ring expansion reaction. So carbenes also give a ring expansion reaction. Carbenes also responsible to give ring expansion reactions. Already I explained in Riemann-Tiemann reaction. Suppose see, if it is a pyrrole, so on treatment with a chloroform in sodium hydroxide, what will you expect? Formylation. It is same we can also expect ring expansion. So what is the ring expansion over here now? Now can I introduce that carbene here or not? Dichlorocarbon is intermediate, that will give like this. Later on this bond migrate here, this will migrate and chlorine is removed. And finally what is the answer? Can I expect 3-chloropyridine or not? It is a ring expansion product. So not only this, even it is applicable for indole. Can I write same mechanism? Suppose if I give chloroform in sodium hydroxide. So what is the ring expansion product? Can I write directly? Now this is benzene and here it is pyridine. On third carbon just introduce chlorine. That is the answer. Same mechanism. So introduce a cyclopropane here and remove hydrogen and chlorine from nitrogen and carbon and finally forms 3-member ring. So not only this, even it is applicable for a normal hydrocarbons. See, this is a hydrocarbon, indene. When indene reacts with chloroform in sodium hydroxide, so what is trapped here now? Dichlorocarbon is going to be trapped here, chlorine, and this is one more chlorine, right? Now, here 2 hydrogen atoms are present, one of the hydrogen atom migrates and chlorine will be removed here. So finally what is the answer? C. Can I create naphthalene or not? Naphthalene, and this is chlorine. That is the answer. Every time what you observe, the common thing is ring is starts expanding when intermediate is carbene. So this is called abnormal reactions. They are not normal reactions. Very abnormal. That's why abnormal Riemann-Tiemann. Okay, this is also one of the product, but this is not major, remember. Clear? That is carbenes. So, after carbenes, next most intermediate is nitrene. Next is nitrene. Chemical reactions of carbenes are over. So, mostly addition reaction, insertion reaction, rearrangement and ring expansion, and one more is a name reaction, that is Siemens-Smith. Okay? So, mostly addition and insertions are most common reactions. If it is a carbene or nitrene, two reactions are most common. They are addition, one more is insertion reaction. Next, nitrene. Next, nitrenes. So, similar to carbene, nitrenes also electron deficient species. So, you can write like this, right, monovalent nitrogen intermediate, monovalent nitrogen intermediate having 4 non-bonding electrons. 4 non-bonding electrons. It is monovalent nitrogen intermediate which will carry 4 non-bonding electrons. Monovalent nitrogen intermediate having 4 non-bonding electrons. Okay. So, nitrenes are electron deficient species. Nitrenes are electron deficient species, unstable and reactive. Nitrenes are electron deficient species, unstable and reactive. So, generally nitrenes are classified into two types. Two types of nitrenes are there similar to carbene. So, here it is, what is one more? First singlet nitrene, then followed by triplet nitrene. Nitrenes are how many types? Two types. Singlet nitrene, triplet nitrene. Monovalent nitrogen intermediate having 4 non-bonding electrons is known as nitrene. It is electron deficient species, unstable, and that is actively reacts with oxygen due to its instability, and it is a reactive species. So, nitrene similar to, it is analogous to carbene. They are also classified into two types, singlet and triplet nitrene. So, what is singlet nitrene? So, it is almost equal to singlet carbene. Singlet nitrene. Is it monovalent or not? Yes. It is also a monovalent nitrogen intermediate. Monovalent nitrogen intermediate having how many lone pairs are present on nitrogen? Having 2 lone pairs. So, they have 2 lone pairs. Now, 4 electrons are there, 4 non-bonding electrons are present, but that 4 non-bonding electrons exist in the form of 2 lone pair. So, can I write like this? This is hydrogen connected to nitrogen. This nitrogen carry how many? 2 lone pair of electrons are present. This is called singlet nitrene. Monovalent nitrogen having 2 lone pair of electrons. So, when this nitrogen carry 2 lone pair of electrons, so you can write like this. See, this is empty cavity, empty orbital, and this is the orbital which carry 2 lone pair of electrons. This is called singlet nitrene. Singlet nitrene having 2 lone pair of electrons and 1 empty orbital, it is behaves as a Lewis acid. It is a de-excited nitrene, otherwise de-excited state of nitrogen. Okay. Now, what is the hybridization of nitrogen in nitrene? 1, 2, 3. Is it sp2? 1 bond pair and 2 lone pairs. sp2 hybridized. And what about geometry here? Now, geometry is not trigonal planar, now it is linear. Why? Because only 1 bond pair is there. And what about bond angle here now? Bond angle is 180 degrees. Okay. sp2 hybridized linear 180. Now, this nitrene you can also write in one more way. So, in your examination they will put a bars over nitrogen. It is also belongs to singlet nitrene. If they given 2 lines, which means 2 lone pair of electrons are present on nitrogen, sometimes they will give one empty box over here like this, which is belongs to singlet nitrene. But most commonly they will give like this only. either this or this way. It is a empty p orbital present on nitrogen and 2 lone pair of electrons present in p orbital. So this is called singlet nitrene. Monovalent nitrogen intermediate having 2 lone pair of electrons. Is it paramagnetic or diamagnetic? Especially singlet nitrene is a diamagnetic species. It is a diamagnetic species. So is it formally neutral? Any charge can you write? No. Nitrenes are formally neutral. We can't any charge. So it is formally neutral species. There is no independent electrons. 4 electrons are present, but they are paid electrons. Independent means free electron. Now 2 lone pairs, that's why it is diamagnetic. Now there is a presence of empty orbital, that's why it is a Lewis acid or not. So you can say it is Lewis acid. Singlet carbon is a Lewis acid due to presence of empty p orbital. Even not only singlet nitrene, singlet carbon also a Lewis acid. Triplet nitrene. Can I define in the same way as that of triplet carbene? You can write like this: monovalent nitrogen intermediate. Monovalent nitrogen intermediate having what they have? One lone pair and 2 free electrons. 2 free electrons are available. 2 free electrons. 2 non-bonding electrons or 2 same spin or parallel spin electrons, and 1 lone pair is present. Total how many electrons? 4. Here 4 electrons in the form of paired arrangement, lone pair. Here 4 electrons, one is lone pair, other is free electron. So you can write like this. See, this nitrogen having 1 lone pair, 2 free electrons, like this you should write. So what is the difference between triplet and singlet? Triplet having, singlet having 2 lone pair, triplet having 1 lone pair, 2 free electrons. Now this can I write in one more way or not? So this is nitrogen, nitrogen having 1 lone pair. Now here see, this is the p orbital where electrons are not involving in bonding, electron, electron. So there is no empty orbital, only half-filled orbital is present. So these 2 electrons are not involving in bonding. Okay, so normally you can write like this. Suppose see if I take s orbital and this is p orbitals of nitrogen. Now here see electron, 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 electron is present. Right? How many electrons are present? So 4 electrons. Generally 1 lone pair of electron is present or not? What is the valence of nitrogen? 3. Suppose here one of the electron having lone pair. Now this electron is bonded to hydrogen, and what about these 2? These 2 are these 2 orbital electrons. So this is NH3. Ammonia. Ammonia, what is atomic number of nitrogen? 7. So 7 means outermost shell carry 1, 2, 3, 4, 5. 5 electrons. So after getting these 5 electrons, one of the lone pair is as it is as a sp3 hybridized skeleton. Then finally 1 electron involving in bonding. If 1 electron involving in bonding, remaining 2 electrons are as it is. So finally can I say what is the hybridization of triplet nitrene? Only 1, 2. Only 1 bond pair, 1 lone pair is there. Hybridization is sp. Is it linear? Yes, it is linear. And what about bond angle? This is 180. Okay. Is it paramagnetic or diamagnetic? So it is a paramagnetic species. Paramagnetic species. Is it any formally charged? No. It is formally neutral. Formally neutral species. paramagnetic species and it is formally neutral. Paramagnetic due to 2 independent electrons. Can you apply multiplicity formula? So what is the multiplicity of triplet? M is equal to, can I apply 2s plus 1 formula or not? 2s plus 1. M is equal to plus of minus 0. So here this 0 and what is this? Plus of 1 or not? So can I write like this 2 into 1 plus 1? Total how much? 3. Plus of minus of cancel. Clockwise, anti-clockwise cancel. Now here plus of 1. 1 into 2. 2 plus 1, 3. In this case, what is the multiplicity formula? If I apply M is equal to, this is called spin multiplicity formula, 2s plus 1. So S carry plus of minus of 0 or not? Plus of minus of 0. So can I write like this 2 into 0 plus 1, finally that is 1. 1 means singlet. So that is structure of nitrine. So in your next class we will discuss what is the generation of a nitrine. Okay? How to generate a nitrine, then what are the general preparations of nitrine and what are the trapping methods and what are the stability factors of nitrine. Finally, chemical reactions of nitrine. Similar to carbon, same chemical reactions are going to be operated for nitrine. Most commonly cycloaddition, then followed by insertion reaction, one dimerization reaction, disproportionation reaction, and selectively some rearrangement reactions are there. Nitrine rearrangement reactions are Hofmann, and one more is Curtius, Lawson, and one more you can also expect Smith rearrangements. They are nitrine rearrangement reactions that we will discuss in your next class. Okay? So take this up to here. So remaining part we will discuss in your next class. So we'll stop here. Take a break. Hi sir.